So, good evening, everyone. Myself, Chaitra Borkar, a PhD scholar from Indian Institute of Technology, Delhi, welcomes you all to the 13th live session, extra session that is being taken for the NPTEL online course, Basic Principles and Calculations in Chemical Engineering, a course instructed by Professor S.K. Majumder from IIT Guwahati. Let's get started. So, some general information about these live sessions that have been conducted and which is being conducted today. That they were conducted on every week, Tuesday from 7 to 9 p.m. The recording links has been shared with you for these live sessions, and you can also access them from my YouTube channel. The structure of this extra session is that firstly we'll go through the overview of all the lectures conducted in this course and then solve some selected problems from the assignments. So we firstly go through the overview of week one. So week one was the introductory lecture. So we started with the definition, history, and role of chemical engineer. So definition means a definition of chemical engineering. So it makes use of the physical, chemical, and biochemical processes so as to generate certain chemicals which are used for the betterment of the humanity. So history of how this chemical engineering subject or course came into being and why it is important. Uh, and then the role of chemical engineer today. So in different fields such as nanotechnology, catalysis, polymeric sciences, a different role a chemical engineer plays in different fields. So then we moved on to the basic features of a chemical process. So here in chemical engineering, you see it is divided into two types. So it is either unit processes or unit operations. So unit processes involve chemical changes, while unit operation only involves physical changes. No chemical changes occur here. So so unit processes can be classified based on either process design. It can be batch, semi-batch, or continuous processes, then based on variation with time and space, and then based on phase contact. So it can be multi-phase, single phase, and so on. Then in unit operations, um, it which involve only physical changes. There can be mechanical unit operations which may involve mechanical separation, mechanical agitation, mechanical transportation, or it can be electrochemical unit operations which have either electrochemical separation, magnetic separation, electrostatic separation, sorry, magnetic separation, and then thermochemical can be separation such as separation such as distillation. Mind you, this is a unit operation, not a unit process, because it is only separating two liquids based on the difference in the boiling points. Absorption without any reaction is also a thermochemical unit operation. Different crystallization, and then there are many more. Then we moved on to the unit systems and dimensions. So different unit systems. So it can be, the SI unit system, then CGS. SI, or you can write it as MKS or FPS or AES system, American Engineering System. Then dimensional analysis. So two methods were discussed: Rayleigh's method or Buckingham pi method. So in Rayleigh's basically the purpose of this dimensional analysis is basically that you suppose there is a variable process variable. Suppose example was taken that for a flow through a pipe, a fluid is flowing through this pipe. So there may be some friction occurring inside because the fluid is flowing, and these pipe have solid walls, so there may be some friction occurring between the fluid and the solid, and because of that the velocity or the flow patterns may vary. So friction, then this friction is then how is it uh, dependent on the different variables, or the friction coefficient, you can say, how is it dependent on different variables. It can be density, it can be velocity, it can be you can say the diameter of the pipe, it can be the drag coefficient, anything. So different variables are there. So how do you find some empirical relation using these two methods? So that is what was sorry, that is what was discussed. And then dimensionless numbers. So basically, you divide all these variables, or you separate these variables in the form of dimensionless numbers. Um, so that is what you see here. The different dimensionless numbers are given. So Reynolds number is basically the significance is also given. So Reynolds number is usually used for a uh, uh, flow through a pipe or a flow over a plate. So you see that it is basically the ratio of inertial forces to the viscous forces. Then so on, different dimensionless numbers were discussed. Then week two discussed the process variables and rate. So variables and properties of material in systems. So we discussed different process variables. It can be state or thermodynamic, they can be dynamic variables, they can be geometric variable, physical properties as variables, and other variables. And physical properties may be either intensive or extensive. So extensive depend on depends on what does it depends on? Amount, and these don't. Also, if you divide an extensive property by extensive property, it gives you an intensive property. Then we studied the expression of concentration and different types of expression. So it can be expressed in terms of density, it can be expressed in terms of mass fraction, it can be expressed in terms of molar density, mole fraction, specific gravity, apparent specific gravity, and API gravity. This is usually for the petroleum liquid products. And then we discuss the pressure and temperature of flow processes. So, firstly, we started with the pressure. So, pressure, we defined this term hydrostatic pressure. So, it is basically rho gh, which is basically the pressure exerted by this column of height h plus the atmospheric pressure. Then we discuss the general manometer equation. So, suppose this is a manometer which has two limbs, limb 1 and 2, and pressure, some atmospheric pressure is also being exerted as P1 and P2. And then whatever the column of, there may be some fluid 1 here, there may be some fluid 2, atmospheric pressure is being exerted as P1, P2. This is the manometric fluid. So you see, we basically we basically assume a datum line, basically a reference line. So it's usually the lower side, lower, it is usually taken as that point where the level of the manometric liquid is lower. So we take this point, and at this point, so basically pressure at this point, because of the virtue of the hydrostatic pressure, the pressure at this point will be equal to pressure at this point. So going by the definition of the hydrostatic pressure, so some pressure already being exerted. This is for the left hand side limb. This is for the right hand side limb. So this is the P1 pressure already being exerted. Then this is some fluid of density ρ1 into g, which is the acceleration due to gravity, and the height of this column d1. Then we go for the right hand side limb. So we equate it to basically the external pressure P2. Then rho2 into G into D2 is basically the pressure exerted by this fluid column having density rho2 or fluid 2. And then we add this extra column of this manometric fluid. So this is rho F. Rho F is the density of manometric fluid into G into whatever the column height is, which is given as H here. If rho 1 is equal to rho 2, basically this fluid and this fluid is same or they have the same density, then we get this formula. So difference in pressure will be basically rho F minus rho 1 into GH. Then we discussed the rate of process. So it can be in terms of flow rate. It can be in terms of rate of momentum transfer. It can be uh, in terms of rate of heat transfer, rate of mass transfer, rate of reaction, and the different relations were discussed. Then we move on to week 3. So it discussed the fundamentals of material balance. Just a minute. Yeah. So it discussed the fundamentals of material balance. So firstly, we started with the principles of material balance and calculation. So we saw the general material balance equation given here. So accumulation within this defined system. So you basically define a system. So anything coming in, anything going out, anything accumulating inside it. If there's a reaction, anything being generated or anything being consumed. So so anything accumulated within the defined system will be equal to input through system boundary. So you suppose also define a system boundary around the system. So input through, so in is this arrow, then output through the system boundary, it is this arrow. Anything generated within the system, if there's a reaction, obviously there will be some generation of some product. If because there is also a reaction, something will be consumed as well, so it will be negative. So anything going out of the system or anything being consumed is basically has a negative sign, and anything coming into the system or being generated has a positive sign. So this is the general material balance equation. So, so how to solve these material balance equation for a given system? The procedure is given here. You can see, firstly, you draw the flow chart and write all the given data. If you know the problem statement, you understand it carefully and then go for drawing the flow chart and write all the given data. Then choose one stream as the basis. It can be input, and then you go for then you go to convert the volumetric flow rates to mass or molar quantities, and then label the unknown streams, then convert all the quantities to one basis. That means if you have some concentrations, so suppose for example, mostly used example is a distillation column. Sorry. So distillation column has some feed, some top outlet, and some bottom outlet. Okay, so this feed will have some mixture. So there will be x1 comma f and x2 comma f. So the concentration of this first component, or you can say xa comma f, xb comma f. So f is basically a mixture of component a and b. Okay, so so the concentrations are can be expressed in a different form. You saw that. So suppose this is in mole percent. Okay, but here the concentrations are given. So this is D stream or distillate, and this is the bottoms. So X A comma D, it may be in mass percent. Okay, uh, based on the problem statement. Suppose. So you have to convert it to one basis. So if you either you convert this mole percent to mass percent or this mass percent to mole percent based on your convenience. Okay, so that is what was meant by this converting all quantities to one basis, and then write the material balance equation, the maximum number of independent equation, and then solve the derived equation to get the unknowns. Okay, then we looked at sorry we looked at material balance on processes with recycle and bypass. uh, so this is the general flow diagram for whether a process has a recycle or a bypass. So what recycle here is, suppose there's a reactor and a separator is attached to the uh, uh, downstream of it. So so we see that from the separator, some stream is being again uh, put into the feed stream. So this is basically recycle. Okay, because there may be some unreacted reactant which you want to again utilize. So this is the recycle stream for that. Then there is some bypass. You don't want some component in this feed to be reacted and to be reacted, so you add it or to, sometimes it is used for maintaining the flow rate, output flow rate. So you use bypass. So you take some cut from the feed and then you bypass it through the reactor and separator. So this amount of feed does not go into the reactor or separator and then is added to the downstream of the separator. Then another thing is purge. Purge is basically there may be some inerts or unused inert components in your feed itself, but you don't want the accumulation of those inerts. So basically, you take out some stream from the whatever is going into the recycle. So you take out some stream so as there is no accumulation of the inerts. Then one more thing is makeup. So makeup is basically uh, you add on more amount of maybe reactant or some other component so as to make up the flow, so as to keep the flow rate coming into the reactor consistent. Then the material balances involving these were discussed. Then we moved on to material balances on combustion. Also, we looked at suppose this is a system. So this was basically for the recycle. So if you consider a system, suppose this is the overall system, okay, which includes inside it the recycle stream. So the overall conversion of A will be whatever is being input minus whatever is being output upon the input, that will be the overall conversion of A. And you see, if you consider only this reactor, so this is called a single pass conversion because there is no recycle stream being considered here. So only single pass through of the feed. So whatever is being input, whatever is being output, and upon whatever is being input. So if you see here, 75 mole per hour of A is there and 75 mole per hour of B is there. You see, here 100 moles per hour of A and 25 moles per hour. So there will be difference in the overall conversion of A and the single pass conversion of A. Okay. So if the reaction is A giving B, so it basically, if you see, basically tells us there is 100% conversion here, and the conversion here may be different because 100 minus 25 upon 100 is basically 75%. So 75% conversion in terms of single pass conversion and 100% conversion in terms of the overall conversion. Okay. Then, if there is a system of reaction. Suppose this is the reaction giving. This is the reaction, uh, and you have another system. You can see that A plus B giving C plus D, and C again. This product is being reacted with another from the previous reactant, giving us this D as well as some other product as well. So this suppose this may be the main reaction occurring and this may be the side reaction. So conversion of A will be basically mole of A reacted upon mole of A fed. Then selectivity of C. So C, D, and E are three products that are being generated through this reaction system. So if you want, this is the desired product here, selectivity of C. So it will be mole of C in input upon mole of E in output. Okay, mole of C in output upon mole of E in output. Then yield of C will be mole of C in output upon mole of A fed. So basically, how much of A is being added, and then efficiency will be mole of C in output upon mole of A reactive. We looked at the material balances on combustion as well. So it basically implies complete combustion. Okay. Um, that means that whatever fuel, so fuel basically has carbon, hydrogen, oxygen, nitrogen. So this completely converts to CO2. Hydrogen completely converts to H2O. If there is oxygen as well, so oxygen will not convert to anything, but N will convert to NO2. It may also have some sulfur, so it will be converted to SO2. So that is what the complete combustion is. And sometimes you add excess of oxygen or excess of air so as to combust your fuel completely. So you may also need to find the percent excess O2. So I'll just rub this all. So suppose there is a fuel known as methane. So some moles of O2, X moles of O2 are required to give us CO2 and H2O. This is the general equation for combusting a hydrocarbon. If you combust a hydrocarbon, it will give you the complete combustion will give you carbon dioxide and water vapor. So, how many moles will be required for the complete combustion of methane? So, you can balance this equation basically. So, if you see the carbon is balanced, hydrogen, however, is if you see here, there are four species of hydrogen, but here 4 units of hydrogen, but here only 2 units. So you add 2 here, so that it becomes 4. Now, if you see if whether O is balanced or not, so you see this is 2O and this is again 2O, so 4 units of O. So, and this is O2, so you add 2 here so as to balance this equation. So basically, you need for complete combustion of methane, you need 2 moles of oxygen. So if you supply, suppose there is 1 mole of methane, suppose, and 1 mole of methane, okay, so if you supply, suppose 3 moles of oxygen, so basically you have 1 mole of oxygen in excess. And this is in terms of moles. It can also be in terms of mass. Okay. So convert the units accordingly. Convert the quantities accordingly. Next, we looked at in week 4 the basic principles of compressible systems. In that, we started with the state equation of ideal gas in calculation. So, ideal gas equation is shown here. So, this describes the behavior of ideal gases. Now, what are ideal gases? This is shown here. So, ideal gas is basically the particles, the constituent particles have no volume. They are basically point particles. Then the collisions are elastic, so there is no energy loss when the collisions occur. And the interactions between the particles are minimum, or there is no interaction as such. Um, so the equation describing the behavior of such gases is, or the ideal gases is basically the ideal gas equation given by this expression. So PV is equal to nRT. Pressure into volume is equal to number of moles into the universal gas constant into the temperature. And different expressions of your universal gas constant in terms of different units were also discussed. Then we looked at the state equation of non-ideal gas in calculation. So not all gases in our nature behave as ideal gases. Uh, so how when and these are termed as real gases. So real gases have a limitation that they may behave like ideal gases at high temperature and at low pressure. At low pressure, there are minimal interactions between the particles because they may be far apart. So we can basically neglect the intermolecular interaction of forces. And at high temperatures, basically there is a high kinetic energy imparted to the molecules. So we can say that the intermolecular forces because of that may also be suppressed. So this is the definition of real gases. These particles have volume. The energy is lost when they collide with each other, and there may be intermolecular forces um, or intermolecular attraction between the constituent particles. So we saw that the real gases, the behavior of real gas, uh, in contrast to the ideal gas, can be expressed in the terms of this Z factor or the compressibility factor, which is basically PV by RT. So we see for PV is equal to nRT or PV by RT should be equal to 1 for the ideal gas. But for the real gas, it basically diverges. Okay. So also we looked at the different phases for a system. So uh, sorry, a substance may some substance, say suppose water, it may exist in solid form, liquid form, or gas form. So with change in the pressure and temperature, how does it phase changes? So that is called your phase diagram. So phase diagram was also discussed. So we see for different pressures and temperature, how does your water changes its phase? So at lower pressure and moderate temperature, it is vapor, and at higher pressure and higher temperature, you see that it comes higher pressure and moderate temperature. You can see, or from 1 atmospheric pressure also, you can see that it comes in the liquid form. And if you compress it even further and at lower temperature, it becomes a solid. So if you keep the temperature constant and you keep on in this region. If you keep the temperature constant and you keep on going up or basically increasing the pressure, you go from vapor to liquid. And from this point, if you keep on increasing the pressure, you can directly go from gas to solid. So this is the sublimation. This is your sublimation curve. This is your vaporization curve or condensation curve, and this is your fusion curve or melting curve. Also, we looked at apart from the ideal gas laws, we looked at sorry. Also, apart from the ideal gas laws, we looked at the Dalton's law. So basically, the sum of the partial pressure of all the constituents in a mixture of gases is equal to the total pressure. Week 5 involved the discussion of basic principle of multi-phase system. So we discussed only one phase up till now. So we look at the multi-phase systems. So this involved the discussion of phase equilibrium. So in that we firstly discussed the Gibbs phase rule. So why is Gibbs phase rule important? Is because it tells us the degrees of freedom. So suppose your system has some components, it has some number of phases, and this is an empirical factor. And if a reaction is occurring, so number of reactions. So this gives us the degrees of freedom that needs to be fixed so as to uh, appropriately define your system. So we looked at single phase equilibrium and we looked at the multi-phase equilibrium. So this is for a single water system. So and this is for the vapor liquid equilibrium. So there are two phases basically. Or you can say this is for single component and this is for multi-component. This is also multi-phase and this is also multi-phase. Sorry. So suppose there is so in this diagram, this is for the phase diagram for water. So you can see that at this position, if we are in this region, the component is liquid, and so the phase is liquid, one phase. There is one component water. So the degree of freedom will be. So F will be one component, one phase plus two, there is no reaction. So basically 2 degrees of, so you need two process variable that needs to be fixed. So here you see that a particular temperature and pressure, the you need to fix the temperature and pressure so as to define your system here. Then suppose if you are at this curve, so at this curve basically two phases exist, but the component is still one. So the degree of freedom will be one component, 2 minus 2 plus 2. So 1 degree of freedom needs to be fixed. So you only need fix either the temperature or pressure. Then here you see at this point, this is called the triple point. So here there are three phases existing at one point. The component is still one. So sorry, it was B5, I guess. Yeah. Sorry. So the degree of freedom here will be, so component is still one, phases are three plus two. So 3 plus minus 3 plus 2 is minus 1. So 1 minus 1 is 0. So this triple point exists at only one temperature and pressure. You may there are no degrees of freedom here as such. So if you increase the temperature and pressure, you will lose your triple point. Then here, this is multi-component um, phase equilibrium which can be shown. So suppose there are two components in a mixture, suppose a liquid mixture, and you keep on increasing the temperature. So there may be some equilibrium between the liquid and the vapor phases. So these are the vapor liquid this is the vapor liquid equilibrium region. And for the same thing, if you keep on increasing the pressure, so it may go from vapor to liquid. We also discussed the term vapor pressure. Vapor pressure is basically the equilibrium pressure of a vapor above its liquid or solid state. So suppose this is a container, this is a closed container. There is some liquid inside this container, which and which involves the evaporation of this liquid to the vapor phase or gaseous phase. So whatever this vapor, whatever the pressure of this vapor of this liquid exerts on the liquid state is basically its vapor pressure. We looked at equilibrium laws, humidity, and saturation. So equilibrium laws involved the discussion of Raoult's law. Raoult's law, Henry's law. So Raoult's law basically tells us that for a non-volatile components, basically for a non-volatile solute, basically we see that this is basically our Dartel's law. Pi, or the partial pressure of that component, is equal to Yi into P. So Yi is again the molar gas phase concentration of this component I, into P is the total pressure YIPT, is equal to Xi into PIV. This is the vapor pressure, and this is the concentration in liquid phase. So these two are different. And Henry's law stated that the partial pressure of the gas above the liquid is basically equal to Xi into H. So suppose, uh, for example, there is a there is some container. This has some liquid filled up to this point, and you need to add a gas. You need to dissolve a gas into this liquid. So how much this gas will dissolve, how much this gas will dissolve into this liquid will depend on the partial pressure just of the gas just above this liquid. So this is uh, basically directly proportional. So this is what is given by Henry's law, which is shown here. So if you keep on increasing the pressure, the more amount of solute will, or the solute basically means here the gas will try to dissolve in your liquid. We looked at saturation as well. So saturation basically, if you look at this figure, so there is a liquid, this is a closed column, and there will be some evaporation and condensation occurring. So the point at which the evaporation has reached the equilibrium is basically said to have saturation. So saturation basically means no more vapor can or no more liquid can vaporize to go into the gaseous phase. The gaseous phase is basically saturated with the vapor. Then we looked at the humidity, which we discussed later. So we looked at the humidity and the saturation and the psychrometric chart. So humidity can be expressed in terms of relative humidity, absolute humidity, molar humidity. So different expressions were discussed, and same goes for saturation. Then we looked at the psychrometric chart. So it gives us basically, so we discussed different terms as well. So wet bulb temperature, dry bulb temperature. So this is the schematic for wet bulb and dry bulb temperature. So if the dry bulb temperature is high, the wet bulb temperature is low, and the dew point is very low. So this is termed as low humidity. Then for medium humidity, the dry bulb temperature basically is constant. If you the wet bulb temperature is high and the dew point temperature also increases, this is called the medium humidity. And if the dry bulb and wet bulb temperature and dew point are close to one another, it is called high humidity. So this psychrometric chart basically gives us, if you fix basically either suppose this x-axis is basically dry bulb temperature, your y-axis is moisture content, so absolute humidity you can say. And if you suppose have these two values, you can get other values as well. So basically whatever the enthalpy of your mixture is, you can find that. You can find the dew point temperature as well. You can find the relative humidity. You can also uh, you can also find what is the specific volume. So suppose these two are fixed at this point. So whatever these purple curves are basically your relative humidity. These green curves are this green line is basically your enthalpy. This yellow line, if you stretch it towards this 100% relative humidity, it tells us it it tells us whatever the dry bulb temperature, sorry, not dry bulb temperature, what is the dew point temperature. So you can find this from the psychrometric chart. We also looked at the process of phase change of condensation and vaporization and discussed the mass balance for these different processes. Week 6 involved energy and its form. So we have discussed some mass balance. We now move on to firstly the principles of energy and then move on to the energy balance. So principles of energy involved the different forms of energy. So different forms of energy can be either kinetic energy, uh, kinetic energy, potential energy. Different types of energy, and these different forms of energy are interconvertible. So basically, the law of conservation of energy states that the energy can neither be created nor be destroyed. It can be transferred from one form to the another. So that is what this GIF shows us. That suppose this ball, which has some potential energy owing to its position, as this moves down from this slope. So this potential energy in this region is being converted to kinetic energy, and at this point the minimum potential energy is there and the highest kinetic energy is there. So just before this point basically, so it will have the maximum velocity just before becoming static. Just before that point, it has the maximum kinetic energy and the potential energy is minimal. So potential energy is basically essentially being converted to the kinetic energy. So we also discussed different types of systems. So different types of systems can be closed system, open system, or the isolated system. So here we see in the schematic that in the closed systems there is no mass transfer, only heat transfer, energy in, energy out. This is your system, and this black curve is your system boundary, and whatever outside of it is termed as surroundings. In the open system, however, there is mass transfer as well as heat transfer, but in the isolated system, there is no energy transfer or the mass transfer. Okay. So energy balance for a closed system basically involves the change in the internal energy. So internal energy is another term. Basically, you have some atoms or molecules, so they have some inherent energy owing to it, their translation, rotation, or vibration. So that is termed as your internal energy. So change in the internal energy plus the change in kinetic energy plus the change in potential energy gives you the change in the uh, heat involved minus the work done, heat supplied to the system minus the work done. So, and for the open system, basically, open system is basically there is mass transfer as well as heat transfer. So the term of rate of internal energy change comes in. So basically, per time, basically, this is a per time unit. So this dot represents the rate of internal energy change, basically per second. So this term this term per time basically. So rate of change of internal energy plus the rate of change of kinetic energy plus the rate of change of potential energy plus this term comes in because there is some flow. So owing to the flow of your fluid or some component in your system, this term comes in. So this is rate of this is volumetric flow rate. Basically, there will be some pressure exerted by the fluid or the component. So that change is equal to Q minus Q dot, this is the rate of heat in minus the rate of work done by the system. So this is basically known as shaft work. So W dot is basically W dot flow plus W dot S. So this basically this term basically is your flow work. Then laws and properties of thermodynamics were discussed. So first law, second law, zeroth law, third law were discussed. So this schematic gives you the gist of that. So zeroth law tells us gives us the concept of temperature. It tells us the two systems in equilibrium with the third system are in thermal equilibrium with one another. Then first law tells us the conservation of energy. Energy can change its form, but neither can be created nor be destroyed. So because of that, you get this general equation. So delta U is equal to Q minus W. You get it from there. So just a minute. So you get this term from the first law. Okay. So just a minute. Yeah. So we now look at the second law. So second law tells us the entropy of an isolated system always increases. So basically, the it tells us the flow of temperature, basically flow of heat, basically the direction of flow of heat. So it will always move from the hotter region to a colder region. And if you want that the direction of heat flow reverses, so you will have to add some work. You will have to do some work to do that. It will not spontaneously go from the colder region to hotter region. So third law then tells us that the entropy of a system approaches a constant as the temperature approaches absolute zero. So at absolute zero, the entropy is basically uh, uh, it approaches a constant value because at this point the molecules are almost at a standstill position at absolute zero temperature. So the entropy of that system will be a constant value. Then we discuss the standard heat of formation basically. So standard heat of formation is basically the heat generated or heat generated when 1 mole of some substance is formed at the standard temperature and pressure condition, which is 25 degrees Celsius and 1 atm pressure. So for this definition, this STP is 25 degrees Celsius, and standard conditions are not STP. Standard conditions are 25 degrees Celsius and 1 atm. So sorry, this schematic shows us that suppose there is substance, say water. So at lower temperature, you can say that it exists as a solid, and if you keep on increasing the temperature, it will show change in phase. So the solid may change to liquid, the liquid may change to gas. So if you keep are also when you are increasing the temperature, basically you are adding the heat energy. So solid, when you keep on adding the heat energy, so this is basically your sensible heat. At a point where it changes the phase, basically the temperature becomes constant, but you keep on adding the heat energy, so that is your latent heat. So at a temperature, constant temperature, whatever the heat is being added to the system is basically your latent heat. Then in the liquid phase, so from solid it converts to liquid. So in the liquid phase, suppose water is at 0 degrees Celsius, or you can say water is at 10 degrees Celsius, and you keep on increasing the temperature to 100 degrees Celsius. So basically, the water is still in the liquid form. At 100 degrees Celsius, however, you are adding the heat energy, you have increased the temperature at 100 degrees Celsius, however, and at 1 atm pressure, obviously, the phase changes from liquid to gas. However, the temperature remains constant at 100 degrees Celsius, but but there is some amount of heat that is being still added at this point, which is called again the latent heat. So it is basically a mixture of sensible heat, latent heat, sensible heat, latent heat again. In the gaseous phase, you can keep on increasing the pressure so as to add the sensible heat. Sensible heat basically the heat that you can sense, and latent heat is basically at a constant temperature, so you can not basically sense. Then we looked at in week 7 the energy balances on non-reactive process. We start with the simpler process or non-reactive process. So we looked at the mechanical energy balance. So this is for an open system. Again, we have discussed this already. If you you know the this mechanical energy balance equation can be used to derive another important relation that is called the Bernoulli's equation. So this is Bernoulli's equation. So it gives us the relation between the change in the pressure energy or the pressure head, you can say delta P by rho, and the change in kinetic energy and the change in the potential energy as the fluid flows through a variation of cross section. So here the cross section is different, here the cross section is different. So how the pressure and velocity will be different from this point to this point, and what is the relation between the pressure as well as velocity at these two different points, it tells us that. The enthalpy balances without reaction can be termed as basically, you can say there is no kinetic energy, no potential energy, so you can say that the mass flow rate into the enthalpy out minus enthalpy in will give you the heat rate. Also, the enthalpy for a system without enthalpy balance for a system, uh, without reaction can be expressed through this formula. So this term is basically your experimental enthalpy of formation that you have um, computed from your experiments. And then this is your into Cp into Dt, basically your sensible heat, and then you add the latent heat. So this is your sensible heat term, this is your latent heat term. So if you change the temperature, so owing to that, if there will be some sensible heat, so mcp delta t, that is your enthalpy again, sensible heat enthalpy, and then this is your you add another term. If there is a phase change, you add the latent heat term. We also looked at two concepts of pertaining to your distillation column. So in the distillation column, there is a feed coming in with suppose there are two components here. So in your feed, so one will be separated from the top column, one will be separated from the one will come out from the richer volatile phase will come out from the top part, and the richer lesser volatile phase will come out from the bottom part. So here, in your distillation column, there are number of feed plates. So how to decide the number of feed plates is through the McCabe-Thiel method. So basically, you have some vapor-liquid equilibrium curve here, and this is the XY curve. Basically, this is your liquid mole fraction X and vapor mole fraction Y. So X is equal to Y on this line. Basically, so liquid mole fraction is equal to your vapor mole fraction. But however, you see that the vapor liquid equilibrium is like this. So you basically firstly fix this Q line or the feed line based on whatever your feed is, whether it is saturated liquid, saturated vapor, partial liquid, partial vapor. Based on that, this Q line is fixed. Whatever the slope of Q line, the slope of this Q line is fixed. So then you have the equation for the distillate part. So this is the curve for the distillate part, and this is the line for the distillate part, and whatever the intersection of this is, you take the whatever the XD is. This is your XD basically, or you can say the mole fraction of your more volatile liquid in the distillate, and this is XD is the fraction of your uh, mole fraction of your more volatile liquid in your bottoms. So here you see from this point you actually start your this is the starting point of your curve for the distillate mass balance equation, and this is the starting point of your mass balance curve line for the mass balance equation for the uh, bottom part. So when you make this structure like this, then you start from this point and you make these lines. So you start from this point, go till the equilibrium curve, and then go down. Then again, repeat the same process. So number of these triangles basically tells you how many number of stages are required to achieve this kind of separation. So in terms of total reflux, basically, so total reflux basically means your D is equal to 0. So D is 0, that means uh, whatever this line is, this red line here is, basically it coincides with your XY line. So because of that, there will be minimum number of, whatever stages are required for between this total reflux or minimum reflux, some usual normal reflux usual normal reflux ratio basically in between this minimum reflux and the maximum reflux or total reflux. So at normal reflux there will be more number of stages, and the minimum number of stages will be at total reflux, while at minimum reflux there will be infinite number of refluxes, infinite number of stages required. Then in week 8, we looked at the energy balances, but for reactive system. So in reactive system, basically you have a generation of some component and the consumption of some component, and with that, uh, heat of reaction is associated. So heat of reaction is again given by this this expression. So this is again an experimentally derived value, and whatever heat or whatever temperature you're increasing or heat you're adding, owing to that, whatever the changes are there, this accounts for that. Then the heat of reaction basically involves this is the formula for heat of formation. So heat of reaction basically involves suppose there are some reactants and there are some products. So A plus B, or I can say P plus Q, giving you R plus S. So these are your, sorry, so these are your reactants and these are your products. So basically heat of formation, and these Ni represents your this Ni represents your the stoichiometric coefficient. So small p into some, I can, sorry, I can write a better equation here. Some small p into p q into capital Q, giving us small r into r plus small s into capital S. So these are the your stoichiometric coefficient, and these Ni basically represent your stoichiometric coefficient and the change in the heat of formation and the change in the heat of formation. So basically, you subtract this from the for the products minus the reactant. So whatever the heat of formation of products is, and whatever the heat of formation change in heat of formation of your reactant is, you subtract basically that, keeping in mind and applying the stoichiometric coefficients as well. Then we also discussed the Hess law. So Hess law is basically given by this schematic. So you see that suppose you want to go from A plus B plus C giving D plus E. So this is one route. There is another route that you can take, which is basically A plus B plus C giving some intermediates X plus Y plus C and then giving us D plus E. So there are two routes that you can take. You know the heat change or the heat of reaction for this route. You know the heat of reaction for this route as well, but you don't know the heat of reaction for this intermediate route. So how you can find out is basically you. So this is basically delta route 1. Okay, route 1 is denoted by R1, and this is basically your route 2. Okay, there is another route 2. You don't know this delta H, but you do know this delta H2, and you know this delta H1. So that basically tells us law of heat summation basically. So delta H1 is basically delta H question mark plus delta H2. So you can find out this delta H question mark is equal to delta H1 minus delta H2. Okay. Then we looked at if there is a reaction going on, what will be the heat of reaction. So this is heat of reaction at standard temperature. You suppose there is some increase in the temperature owing to this reaction. So reaction may be endothermic or exothermic. So if it is an endothermic reaction, the temperature will rise. And if this is an exothermic reaction, sorry, the temperature will rise. If it is an endothermic reaction, the temperature will fall. So because of that, the change in your specific heat of your components. This is your these are your products minus the change in the specific heat of your into the change in the temperature of your reactants gives you the heat of reaction at higher temperatures other than your standard state. Also, heat energy balance with heat of combustion. So, heat of combustion can be found out basically from this calorimeter. So, this tells us the how much heat is evolved when some uh, fixed amount of your combustible material is ignited. So here you see the heat of reaction in terms of heat of combustion is different from what is given in the product. So what different from what is given in the heat of reaction in terms of heat of formation. Please keep in mind this subscript. So this is F is for formation, this is for combustion, and here you see the terms are reversed. So here the first term is reactant and the second term is products. Keep that in mind. Also, this this bomb calorimeter can be operated at either constant pressure and constant volume. So constant volume experiments involve basically the change in internal energy basically gives you the heat supplied at constant volume or heat generated at constant volume, and the change in the enthalpy gives you and this is at constant volume and this is at constant pressure. So this bomb calorimeter experiment can be done at constant volume or constant pressure. So this heat generated at constant pressure is equal to change in enthalpy. Heat generated at constant volume is basically equal to your change in internal energy, and bomb calorimeter is usually operated at at constant volume. And the difference between these two, uh, heat rate at constant pressure and heat generated at constant pressure and heat generated at constant volume, is basically equal to the change in the moles of your gaseous product into R into T. So basically, suppose a fuel is in gaseous state, suppose methane, and O2 is also in gaseous phase. It gives us CO2 also in gaseous phase. However, the H2O can be in the liquid phase or gaseous phase depending on the temperature generated. So keep in mind, only the gaseous components are considered. Change in the moles of the gaseous components are considered here. In week 9, we looked at the balances on transient process. So up till now, we were looking at the steady state process. So the material balance equation, general material balance equation, is accumulation is equal to input minus output plus generation minus consumption. So in this case, in the steady state, this accumulation term is zero because there is no accumulation or change in concentration with respect to time. So this is in steady state. However, in the unsteady state, or the it is also known as transient processes. So in that case, you cannot neglect this accumulation term. So the overall material balance or the complete material balance equation needs to be considered here. I minus O plus G minus C is equal to A. And then that material balance equation is given here. So delta M. So suppose this is a system. Some mass is flowing in, some mass is flowing out, some reaction is also going on here. So at different with some change in time, whatever mass is coming in that duration of time minus whatever mass is going out in that duration of time, plus whatever rate of generation of that product is there in that duration of time minus whatever if it is being consumed in that duration of time. So the change in mass basically is given by this relation. And then you get dm by dt. Basically, your mass is changing with respect to time in transient processes. It gives you m dot in minus m dot out plus rg minus rc. So, unsteady state energy balance then involves. So, this is for material balance. We now go for energy balance. So, energy balance will now involve again the accumulation term as well. So, this is the relation given for this. So, change in the energy with respect to time gives us the change in the enthalpy or the heat content, the change in kinetic energy, change in the potential energy, plus the heat rate minus the work done, rate of work basically. For closed system, however, because of this term almost equal to zero, we see that dE by dt is equal to du by dt is equal to dh by dt. And du by dt owing to this becomes then uh, the change in enthalpy, basically enthalpy coming in minus enthalpy coming out, plus the heat rate minus the shaft work rate. Week 10 looked at the computational techniques. So suppose you have an experimental data with you and you want to fit it to some model. It can be any type of model. It can be parabolic, it can be linear, it can be cubic. But here we look at the linear fitting. So suppose there are two variables y and x, and you have some experimental data with you, and you want to fit it you want the linear fit of it. So basically, what you do is that you firstly develop some model. This is small yi is basically your model given by this. So in this case, you don't know these coefficients right now. The unknowns are this b0 and b1, and you know yi at each point basically. So the error will be yi minus yi. So at this point, at this xi, the error will be this yi. This is your yi minus your small yi. Okay. So, which is your observed response. Observed response basically pertains to your experimental value, and predicted response basically based on your model which you have done. So, so as to get the best fit is basically you minimize the square of these error, not the error. You don't minimize the error, you minimize the square of these error, and then you get these coefficient B0 and B1 from this linear fitting, and then that line which you construct using this equation gives you the best fit for your experiment, best linear fit for your experimental data. Also, how to solve the non-linear algebraic equation system is if you have when you have one equation, so you apply the Newton's method, and this is basically an iterative method. So you need to give an initial guess so as to solve your non-linear algebraic equation, and you have to give some convergence criteria as well. So when this convergence criteria is met, you get your solution. Also, if you have a set of non-linear algebraic equation, this is the formula that you get. So this is at some iteration k. So the previous iteration solution minus the Jacobian at the previous solution, inverse of that Jacobian into your system of equation. So this is the system of equation. So f is dependent on number of variables, and this function or which is equal to your equation f1, equation f2, and so on till fn. So the Jacobian is given by this representation. So basically, what you do is there are number of independent variables, and the dependent variables are these f1, f2, fn. Okay, so basically what you do is firstly you take the derivation of f1. This first row is basically all your f1 with respect to all the variables involved. So x1 to xn. Then this goes for f2 for with respect to all variables, and then till so on till your last function fn with respect to in this row with respect to all your independent variables. Okay, so this is for the system of this is for single equation. This is for system of equation. I mean simultaneous equations that are active. Then and this this represents your Newton method for a single equation. Basically, you know, this is your function. So this is your y is equal to fx basically. So and this depends on x. So you need to find what is the solution. So solution of this fx will be at that point where y is equal to 0. So x uh, at that x where y is equal to 0 is your solution. So you take some initial guess. Suppose this is your initial guess. And if you apply the Newton's method, basically what you do is it gives you, it follows this path, basically your tangent. So, sorry. So if you look at this Newton's method, this is f dash xi. So basically this is the slope of your curve. So owing to this term, basically you follow this path, and then you get this another solution. So this is your first iteration. After this first iteration, then you get this solution. After this, this was your second iteration. So whatever after the two iteration, you got this solution. After a number of iterations, you may reach to your solution. So this is the representation, graphical representation of the Newton's method. Then we looked at numerical integration. Numerical integration basically gives you the area under the curve for definite limits. Okay, so suppose there is a curve, but you don't know the function of that. So, but you don't know the mathematical representation of this curve. So, how to find the area under this curve? So, integration gives you basically the area under the curve, but this is the numerical form. So, there were two methods discussed. So, this expression is for trapezoidal method. and this is for Simpson's method. So this basically approximates. So there may be number of intervals that you need. There may be data points at that. So it approximates these sections into a trapezoid, and then whatever the area of each trapezoid is, it adds that and gives you the total area under the curve. And the Simpson's method basically, sorry, Simpson's method is basically you have this curve and it approximate each section, whatever the interval you have given, it approximate each section as a parabola, and that's how you get this relation. Mind you, this n is number of intervals and not number of data points. Week 11 discuss the computer-aided balance calculation. So to make such computations using your software, you firstly need to know whether your system is solvable or not. So that you can do from the that you can compute from the degree of freedom analysis, and you from that you get the number of degrees of freedom. So number of degrees of freedom, the expression is given here. We have done this, I guess, 2 weeks back. So number of unknowns plus the number of independent reactions minus the number of independent equations. So this number of independent reactions comes into play when there is a reaction going on. Otherwise, this doesn't come into play. Minus number of independent equations minus number of useful auxiliary relations. So a system, suppose this is a system which has a mixer, and attached to two distillation columns in the downstream. So you see whether you define this unit. So how many number of degrees of freedom for this system, how many number of degrees of freedom for this system, or how many number of degrees of freedom for this system, or you define this overall system as well. So how many number of degrees of freedom for this overall system you can find out using this formula, and based on your problem statement basically. So the how you can do your degree of freedom analysis is shown in this flow chart. So you firstly draw the process flow after understanding your problem statement correctly. You draw the process flow diagram, then label each stream with components present. Write the independent equations for each unit. So this unit have some will have some material balance, energy balance equation. Then mark the unknowns. Then write the auxiliary relations, if any, they may be physical relations or others, and then perform the degree of freedom analysis. We also looked at the process flow sheeting and code. So basically, process flow sheeting is uh, to perform the computer-based calculations of steady-state heat and mass balance, sizing and costing for a chemical process. So basically, it reduces our effort. Basically, you are doing some computational computer-based calculation, so it reduces your effort basically, and it can be done in number of processes, which involves solving of the linear or non-linear equations. And then we looked at week 12, which the live session was done yesterday itself. So case study for a process. It involved the cumin production and phenol production. So we looked at the flow sheets of these different these two processes. So this is for cumin production. We looked at the reaction between basically it's a reaction between propylene and benzene, which gives the main reaction as you know cumin. But there is also a side reaction occurring between propylene and cumin, which gives us DIPB or diisopropyl benzene. So whatever this is the tubular reactor where the main reaction occurs, and after that the separation processes are shown here. Also, mass balance and energy balance for these for this whole flow sheet was done, um, which was discussed in an elaborate manner in the lecture itself. Then the the production of phenol from the benzene sulfonation process was discussed. This is the simplified flow sheet that I have taken from the internet. So it involved the reaction between benzene and firstly fuming sulfuric acid, which gives us the benzene sulfonate, then benzene sulfonate, then goes into the neutralizer to gives us sodium benzene. Sorry, this is benzene sulfonic acid. This benzene sulfonic acid uh, gives the when neutralized gives the sodium benzene sulfonate. Again, it goes to the fusionator, which is a which is a process which has a higher residence time. So in the fusionator, basically you add NaOH and this reacts with sodium benzene sulfonate to give you sodium phenoxide. And then the sodium phenoxide is acidified in the presence of H2SO4 and SO2 to give you the crude phenol, and crude phenol is taken to the vacuum distillation column to give you a purer form of phenol. And also the bottoms of this acidifier is taken into the seam stripper so as to give you more of the so as to recover more of the phenol, which is again taken into the your vacuum distillation column. And whatever the salts are here, because this will be the mixture of sodium sulfite and phenol, so this sodium sulfite basically is enriched using crystallizer and then through centrifugation and then recovered and then again put into our neutralizer. So we now will solve the some selected assignment question. So this was from assignment 2. So a solution of specific gravity 1 consists of 35% A by weight and the remaining B. If the specific gravity of A is 0.7, the specific gravity of B is. So we'll solve this. We know specific gravity is basically density of say some liquid upon density of the reference liquid, which is usually water for liquid. So rho W is basically, you know, rho W is 1 gram per milliliter. Okay. And then rho L basically will be, or rho solution in this case will be specific gravity of solution into rho W. So basically 1 into 1 is 1 gram per milliliter rho of solution or density of solution. So you found out the density of solution. Let's say you take a basis is 1 gram of your solution. Okay. So 1 gram of solution means you know the mass fraction of your A. So then from this you can say 0.35 gram is A and remaining is B. So 0.65 gram is B. You now know the mass of these components. However, you know the specific gravity of A and you know the specific gravity of B. So you can say the volume of solution. If these volumes are additive, okay, volume of solution will be volume of A plus volume of B. Keep in mind if these volumes are additive. Sometimes if you add volume of A plus volume of B, volume of some volume of A and some volume of B, it will not be equal to this relation. But in this case, the volumes are additive. Okay, so in this case, VA, how can we find out VA? So we know the specific gravity of A, which is 0.7. Or you can say the rho of A will be again from this exercise that we did is basically 0.7 gram per milliliter because the rho of W is 1 gram per milliliter basically. Okay. But we don't know rho of B because we don't know SG of B. So we know mass of A by rho of A. So basically rho is mass by volume. So rho of A is equal to mass of A by volume of A. So volume of A can be found out using this relation. Volume of A is, sorry, mass of A upon density of A. And this is mass of B upon density of B. And this is your volume of solution. So volume of, what is the volume of solution? So if 1 gram of solution is taken and the density of solution is 1 gram per milliliter itself. So volume of solution again will be mass of solution upon density of solution. So mass of solution from the basis is 1 gram upon 1. So again 1 milliliter. Okay. So 1 is equal to mass of A is, what is mass of A? 0.35 upon rho A is your, you are given 0.7 plus mass of B you know 0.65 but you don't know what is rho B. So from here you can find out what is rho B. So it comes out to be 1 minus 0.35 by zero point 0.7. This gives you zero point 5 upon point, so 0.65 upon zero point 0.5, basically it gives you 1.3, and then Sg of B will be basically rho B upon rho water. So again 1.3 by 1 gives you 1.3 itself. 1.3 is the answer. Next, we look at another question from assignment 2. Heat is transferred from a wall having a thickness of 2 millimeter conduction only. One side of the wall is maintained at a constant temperature of 100 degrees Celsius. Another side is maintained at 25 degrees Celsius. The thermal conductivity of the wall is 0.5 watt per meter Kelvin. Calculate the heat flux kilowatt per meter square through the wall conduction only. So the rate of conduction, if you can say heat rate of conduction, is basically given by this formula. This is the Fourier's law, basically, minus K A delta T upon delta X. So we need heat flux, so that will be basically Q dot upon A. Okay, so this is 100 degrees Celsius, this is 50 degrees Celsius, this is T2, this is T1, and there may be some heat transfer. This is the temperature profile. So you are given the conductivity, which is your small k, so which is 0.5. Area goes here. Delta T, you know, 50 minus 100. If there is a negative sign, basically, and then delta X is your this thickness, basically. So it is in, these are in your degree Celsius. This is in watt per meter per Kelvin. You need to keep in mind this is a meter unit. So here you need to do 2 into 10 to power minus 3. So, oh, not 50, sorry. This is not 50. This is 25. This is also 25. My bad. So, minus 0.5 into 25 minus 100 upon 2 into 10 to power minus 3 gives you 18750 watt per meter square. Okay, so what will it be in kilowatt is 18.75 kilowatt per meter square. So the correct answer is 18.75. Next question, it is pertaining to assignment 3. So this is reaction A giving 2B plus C takes place in a reactor F figure. The reactor effluent is sent to a separator. Then the overall conversion of A is 95%. The product stream from the separator consists of B, C, and 0.5% of A entering the separator, while the recycled stream consists of the remainder of the unreacted A and 1% of B entering the separator. Calculate the percent conversion of A in the reactor. So you know the overall conversion. So overall conversion is basically the boundary will be like this. Okay. So whatever product is coming out, basically, so suppose you take feed as basis as 100 moles, sorry, basis as 100 moles of A coming in this fresh feed. Okay. And the overall conversion you know is 95%. So basically in A, or you can say, firstly you define the unknown stream. So this is your product, this is your separated stream, this is your recycled stream, this is your reactor effluent, okay, and this is your mixed feed, because this is whatever is being recycled is added to the fresh feed. You can term it as F. So F plus R gives you M. Okay. So the moles of A in P you don't know right now. Okay, but you know the moles of A in F. Okay. So the overall conversion is basically given by this formula. So whatever in minus out upon in into 100. So it is given 95, or you can write 0.95 if you get this 100 here. In is 100 moles, out you don't know, so this is your N of A in P, upon in is again 100, so you get Na comma P as 5 moles. Okay. Now these 5 moles of A in this product is basically you are given this relation that 0.5% of A entering the separator. So the product stream from the separator consists of B, C and 0.5% of A entering the separator. Basically, the mathematical representation of that is basically Na in E. This is entering in your separator, okay? Na in E, the 0.5% of that. 0.5% of that is your Na comma P. Okay. So from this you can find out NaE again. So this is 5 upon 0.5 into 100. So this comes out to be, sorry, yeah. This comes out to be 1000 moles. Okay. Na comma E. So this is your whatever A is coming in into your separator. So I can make this diagram here. This is your separator. So this is your E stream. This is your P stream. This is your recycle stream. So basically E is equal to P plus R. So NaE is equal to Na comma P plus Na comma R. Okay. So basically what you get is you can get Na comma R from here. So Na comma R will be Na comma E minus Na comma P. You know both these values. So 100. Oh, this is not 100. Sorry. This is 1000 moles. So 1000 minus 5 is 995 moles. Okay. So you see here that this 995 moles of A are being added in this from this recycle stream. 100 moles of A are being added from this point. So at this mixing point, 995 of A, 100 of A. So this gives you 1095 moles. So basically your Na comma M is basically 1095. Okay. So in your reactor basically this is your M stream and this is your E stream. So E is your, how much was that? NaE was 1000 and coming in is 1095. So you can find out the reaction percent conversion of A in the reactor. So that will be 1095 minus 1000 upon 1095 into 100. So that will come out to be 8.67%. Okay. So basically what the question asked you was the percent conversion of A. So you did not know this how much of A is in this stream and how much of A was in this stream. M, but you know how much of this, how much the conversion, overall conversion of A was. So if you take some basis, you can find out firstly A in product. You know, you were also given the expression of relating the A from this to this. So you then found out this. Then whatever the remaining was this recycle stream. So because of the material balance or at this separator, then you added that to your fresh feed to get this finally. And then you can find out the conversion of A in the reactor. So 8.67%. Next, it pertained again to the assignment 3 for an elementary reaction A plus B being C plus D, 1 gram mole of A and 1 gram mole of B reacted to form C and D. At reaction temperature T, the equilibrium reaction constant K is 1. Calculate the mole fraction of A at equilibrium. So let's suppose A plus B gives you C plus D. Okay, this will be a reversible reaction. So at time t is equal to 0, there was 1 gram mole of A, 1 gram mole of B, and there were 0 moles of C and D. Then at time t equilibrium, basically, you get, you remove some, basically, some amount of A is being reacted. So let that be the amount reacted will be X. So 1 minus X will be remaining. Again, for B, it will be 1 minus X. Then amount of, because of this stoichiometry, you see the amount of C formed will be X, amount of D formed will be X. So this is your moles. You can say moles of A, B, C, and D at equilibrium. So the total number of moles is 2. If you add 1 plus 1 plus 0 is 2. If you add these, 1 minus x plus 1 minus x is 2 minus 2x basically, and then you minus these 2x, so basically it again gives you total number of moles are unchanged, it is 2. Uh, then at equilibrium basically, so at equilibrium you have some equilibrium constant, so it is basically the ratio of the moles of product upon the ratio of the product of moles of product upon the ratio of product, ratio of the product of your concentration of your whatever product is, and upon the product of your concentration of reactant. So x into x upon 1 minus x into 1 minus x. So this is your 1. Okay. So basically x square upon 1 minus x whole square is 1. So from this you can find out x square is equal to 1 plus x square minus 2x. So x will get cancelled. 2x is equal to 1. So your x comes out to be 0.5. So this is your moles of C formed. So how many moles of A at equilibrium will be 1 minus x, again 0.5. This is your moles of A at equilibrium, not the mole fraction. So mole fraction of A will be mole fraction, or you can say you denote it as how you can denote it. Sorry, n of A, suppose. So that will be basically x of A upon x total. Sorry, sorry. Mole fraction of A. You can write this as moles of A upon total moles. So total moles is 2, and this is basically your Na. This is a variable, okay? This is x. This is not your mole fraction or anything. So Na is again 0.5 upon 2, which gives you 0.25. So the correct answer is this D part, 0.25. Okay. Keep in mind you have been asked mole fraction and not moles of A. So don't select this 0.5. Then a question from assignment 4. Basically, the gas having a pressure of 3 bar is heated from 0 degrees Celsius to 5 degrees Celsius, which is then consecutively compressed to one third of its original volume. The final pressure value is. So you can apply the ideal gas equation here. So there will be some P1, V1, T1, and at state 2 there will be some P1, P2, V2, and T2. So because PV is equal to nRT, if there is a constant amount of gas, N is constant, R is constant, and there is some variable temperature. So you can say P1 V1 T1 is equal to P2 V2 T2 because this nR is constant. Okay, so we know P1 is 3 bar. Okay, this is your we don't know this P2. We don't know V1, but we know the relation of V2 is basically V1 by 3. T1 we know it's 5, it's 2, 7. This is in degrees Celsius given to us in the question, but we convert it to Kelvin, 273 Kelvin. And this is your final temperature, which is 823 Kelvin. So you can solve this relation to get your final answer. So basically, you keep the units consistent. So 3 bar into V1, we don't know basically. The T1 is 273. Then we have here P2, we don't know, but we know the relation of we know V2 in terms of V1. So it will be V1 by 3 upon T1 is 823. So we can compute this P2 from here. So basically V1 gets cancelled. This 3 is in denominator, so it will go up. So 3 into 3 into 823 upon 273 basically. So this gives us roughly around 27 bar. If you take the temperature as 273.15 and this as 823.15, this is the more accurate value of temperature. So you will get exact 27 bar. So the correct answer is 27 bar. Then a question related to your assignment 5. If the concentration of CO2 dissolved in the sparkling water, just a minute. Yeah. So a question related to your assignment 5. The concentration of CO2 dissolved in the sparkling water in a closed soda can is 0.75 mole per meter cube. Then find out partial pressure of CO2 in bar in the can at 25 degrees Celsius. Henry's law constant for CO2 in the water at 25 degrees Celsius is 0.34 mole per meter cube bar. So you know a relation for Henry's law is basically Pi or partial pressure of that component into the concentration of that constitute or the mole fraction of that component in the liquid phase into your Henry's constant at a particular temperature. So another way to express this Henry's law is suppose we have Ci into Pi is equal to H. So if you see from here, this is unitless basically. So your Henry's constant unit is in some units of pressure, say bar, ATM, or you can say Pascal. But from here you can see that this is concentration, so it can be mole per liter. This is in your bar, suppose. So the unit of Henry's constant from here will be mole per liter into bar. Okay, so that is what is given here. Mole per meter cube bar. Meter cube is again a unit of volume and liter is also a unit of volume. So from here you can see that you are given the concentration 0.75 mole per meter cube is equal to, you don't know the partial pressure Pi into your Henry's constant is 0.34. So if you solve this, you can get your Pi. So this comes out to be 2.20 bar. You see the units are consistent. This is mole per meter cube. This is mole per meter cube bar. So if this goes in the denominator, bar comes up. So the unit becomes consistent as bar. So the correct answer is 2.2 bar. Next question from assignment 6. A stream of nitrogen flowing at 100 kilomole per hour is heated from 303 Kelvin to 373 Kelvin. Calculate the heat transfer in kilowatt, which is given to us. A hint is given to us. 1 joule per second is 1 watt. And the Cp for nitrogen, you are given this expression. So Cp can be expressed in this form. So this is some empirical relation. So basically, your heat transfer will be mCp dt, and from T1 to T2, and this is m dot, basically your heat rate. Okay, so we know 100 kilomole per hour, but this is in joule per second. So basically, you convert this first to kilomole per second. So this will be 100 upon 3600. Sorry, oh, sorry, kilomole per second. Or you can, what you can do is 100 into 10 to power 3 mole per second. So basically 27.778 mole per second. So this is your the units are now consistent. So Cp is basically, you are given 29.5909 minus 5.141 into 10 to power minus 3 T plus 11.1829 into 10 to power minus 6 T square minus 4.968 into 10 to power minus 9 T cube. So this is your Cp term into dt, and this is your integration from 303 Kelvin to 373 Kelvin into 27.778. So this is your heat rate, heat transfer rate. Okay. So uh, dt. Okay. So you need to integrate this. So this term becomes, after integration, basically this is the limit 303 to 373. So 29.5909 into T, okay, minus 5.141 into 10 to power minus 3 T square by 2 plus 11.1829 into T cube by 3, because this is integration. After integration, it does that. 4.968 into 10 to power minus 9 T4 by 4. So you put in the limits, you get the answer as 56.27. I'll just calculate it here for your, just a minute. So I can write this here as 2.27.778 into the first term comes out to be 2071.363, then minus it will be 5.141 into T1. So after putting the limits, so T square by 2, this is T2 and T1. So this basically becomes T2 square minus T1 square by 2, not the whole square of that. Keep that in mind. So 373 square minus 303 whole square upon 2. So it's basically 121 point again 636. Then you add another term 11.1829 into 10 to the power minus 6, 373 cube minus 303 cube, plus 89.75 minus this is 4.968 into 10 to the power minus 9 into 323 to the power 4 minus 303 to the power 4. That gives you 13.57. 13.57. If you solve this, you get your answer as 56,275.4 joule per second. You want it in kilowatts or kilojoule per second basically, so that will be 56.27 kilojoule per second or 56.27 kilowatts. Next question from assignment 7. An airplane flies through the sky where the air flows horizontally over the airplane wing at a speed of 110 meters per second on the top and 80 meters per second on the bottom of the wing. The air density is 1.2 kg per meter cube and the wing is 9 meters long and the average width of is of 3 meters. What is the pressure difference on the two sides of the wing? So basically, suppose there is an airplane wing of this dimension, suppose, and the average width is 3 meter. Above this, on the top is 110 meter per second velocity, and it is the bottom of this is 80 meter per second velocity. So you need to find the pressure difference. So you basically apply, if you are given the different velocities, you need to find the different pressure. So you apply the Bernoulli's equation. So delta P by rho plus delta U square by 2 plus G delta Z is equal to 0. In this term, we neglect this, in this problem, we neglect this delta Z, which is basically a 3 meter, which is a relatively lower value. So, or the relatively insignificant values in the, when compared to these high values. So delta P by rho will be minus of delta U square by 2. So this comes out to be 80 square minus 110 square upon 2 into your rho minus like that. So this comes out to be so 3 4. So delta C is your 3420 Pascal. So this is your answer. Next question is cylinder fitted with a movable piston is filled with gas. The amount of to 20.920 kilojoule of heat is transferred to gas to raise the temperature by 150 degrees Celsius. The gas does 50 joule of work in moving the piston to its new equilibrium position. What should be the change in the internal energy of the system? So there is a cylinder fitted with a movable piston. So the amount of heat transferred to the gas to raise the temperature. Uh, so there is some heat being added. There is some work done in moving the piston to its new position. So there will be some work done by the system. So you see there is no kinetic energy, no potential energy. So basically it's basically delta U is Q minus W from the energy balance equation. So there is no kinetic energy, no potential energy of this system. This system, not this piston. This system, there is no kinetic energy, no potential energy. Change in kinetic energy or change in potential energy, only the change in internal energy. So you are given in kilojoules, so convert that. So 20920 joules minus 50 joules. So this gives you so 20870 joules or 20.87 kilojoules. So this is your right answer. Next question from assignment 8. The standard heat obtained from the bomb calorimeter at 298 Kelvin is minus 1368.56 kilojoule per mole. The standard heat of combustion of ethanol vapor is as follows. So you need to basically find out the standard heat of combustion. You know the standard heat obtained from bomb calorimeter basically. So this is basically QV and you need to find out QP basically. So or you can say this is your delta U and this is your delta H. You need to find out. So you know delta U and you know delta H. So delta H minus delta U is your delta NGRT. So so firstly you need to find out the change in the moles of the gaseous component. So this is product minus reactant. So 2 minus 3. So this comes out to be minus 1 basically. So 1 into 8.314 into 298 because this is at 298 Kelvin. You don't know delta H, but you know delta U. So it's negative of 1368.56 on this side. Delta H is this. So delta H comes out to be 1368.56 minus 8.314 into 1 into 298. So this will be your answer. Sorry, this negative sign will be here. So it comes out to be Please mind you, this is in kilojoule per mole. So we need to divide this by 1000 because this is in joule per mole per Kelvin. So you need to divide that by 1000. So sorry for that. So this comes out to be minus 1366.088 kilojoule per mole. Next question, calculate the value of the difference between the heat of reaction at constant pressure and volume for the given reaction. Basically, QP minus QV is equal to delta Ng RT. So basically, you need to find out this QP minus QV, which can be computed through this expression. So delta Ng can be computed 12 minus 15. So minus 3 into R into T. So that will be minus minus 3 into 8.314 into 298. So this is in joule per mole per Kelvin. So 7432.7 joule. Okay. So this will come out to be 7.432 kilojoule. So this answer, or you can say this will be minus because this is delta Ng is minus. Next question, a pan of water containing 1 liter of water at 0 degrees Celsius is placed on an, this is from assignment 9, so this had unsteady state, energy balance and mass balance. This week had a discussion of unsteady state, mass balance, energy balance. So 1 liter of water at 0 degrees Celsius is placed on an electric heater where the heat is supplied as Q is equal to 2500 joule per second to increase the water temperature to 60 degrees Celsius. Calculate the time required to raise the temperatures and specific heat capacity and constant pressure at constant pressure is given to you. So from the energy balance itself, du by dt, this is the accumulation of internal energy basically. So this will give us, because there is no heat flow, because there is no flow basically in the system, so Q into delta. So this Q dot minus, and this is also 0, there is no shaft work. So this is your energy balance equation for this system. Also, you can write U as rho V Cp. And volume is constant here, rho is constant here. Uh, Rho V Cp into T basically. So T is not constant here, so we get rho V Cp out dt by dt is equal to Q dot. So this, just a minute, let me just check something. Yeah. So you basically integrate this from T1 to T2 is equal to Q dot by rho V Cp from 0 to some time. Time at that time temperature is T2. So T2 minus T1 gives you Q dot upon rho V Cp into T basically T minus 0. So you can find out time from this relation. So T2 and T1 is given to you 60 minus 0, 60 degrees Celsius into Q dot is given to you 2500 joule per second upon rho is your, you can say 1000, or you can say 1 gram per milliliter basically, and your volume is given to you 1 liter, so you can take this as 1000 milliliter basically. into your Cp is 4.16. Because this is in joule per gram, that's why I took the density in gram per milliliter. Okay, so into your time. So time comes out to be, keep the unit consistent, that's why the conversion is required. 1000 into 4.18, not 4.16. And 2500. So the time comes in your 100.32. This is your second. Okay. To convert it to minute, you divide it by 60. So 1.672 minutes. So the correct answer is, keep that in mind. Whatever the unit is, you need to keep that consistent. The answer is expected to be in minutes. You compute the answer in your second from this equation basically. So you need to convert that. From assignment 9, another question: a single effect evaporator is fed with. So we make this system here. Evaporator is fed with some feed of 10,000 kg per hour of weak liquor containing 15% caustic. So uh, XC in feed is, this caustic is 0.15 uh, by weight, and is concentrated to get thick liquor. So some stream L is coming out, which has XC in L is zero point 0.4. So basically, it is concentrating, it's basically enriching this concentration of this caustic in this solution, this evaporation, what is doing is. And then there will be another stream, B. So this is basically your vapor. It will not have any of your caustic. So this is another stream. Calculate the rate of thick liquor formed in kg per hour. So this is given to us as not 15,000, 10,000 kg per hour. So from the material balance equation, overall material balance, we get F is equal to V plus L. But we don't know V, we don't know L. We know another this is OMB. And another component material balance equation in terms of caustic, we can get XC into F into XCF into F. There will be no component in V, so this is 0 plus X C comma L into L. So after solving this, you can get it. This equation itself, you can get it. So we know XCF is 0.15 into 10,000. XCL is 0.1, 0.4 into L. So from here, you can get the L. So it gives you 3750 kg per hour. So the correct answer is second option. Now in sewage treatment plant, a large concrete tank initially contains 4,40,000 liter of liquid and 10,000 kg fine suspended solid. To flush the material out of the tank, water is pumped into the vessel at a rate of 10,000 liter per hour and liquid containing solids leave at the same rate. Estimate the concentration of suspended solids in the tank at the end of 3 hours. So basically what you have is a tank. There is a constant agitation here. Already you have some solid and some liquid. There is some concentration of this fine suspended solid in this liquid. Okay. You now add in another, you add pure water. Okay. This is pure water, 10,000 liter per hour. You add in the water, and then at the same rate it is being taken out. Okay. So you are given the material balance equation here. Now this is the transient balance because there was already accumulated some mass inside the tank. So there will be an unsteady state in terms of material balance. So this is what your relation is given to you. So we can take V out. So V dc out basically. So we can say that because there is a constant agitation, the concentration in tank will be is equal to C out. So this is C out, this is C in. There is no C in. Basically, C in is 0. So so minus of V dot out into C out, because this term is 0. So if you integrate that, so minus V dot out upon V into dt 0 to 3 hours and dc out upon C out. So we don't know, this will be C. This is, we know the initial concentration inside the tank is basically 10,000 upon 4,40,000. Yeah. So this is your concentration, initial concentration. So after solving this, you get ln C minus ln of 1 by 44 basically, because this gets cancelled. So and V out is again your 10,000 liter per hour, and V is your 4,40,000 again, and then into your 3 hours. So if you solve this, so basically whatever the expression comes in, you have to take the anti-log because this is an ln. So C comes out to be, after taking the anti-log, 0.021 kg per liter. So don't forget to take anti-log. So the correct option is second one. Next, from assignment 10, we have, so this was about numerical methods. So calculate this expression using n is equal to 4. So we are not given a data, however, we are given the fx and we need to find out x. So x, fx. So, and we are given initial and final x also. So first will be 0 and there is 1. The number of interval is given to us as 4. So basically h will be 1 minus 0 upon 4. This is the width. So it comes out to be 0.25. So the second point will be 0.25. Third point will be third point will be 0.5. Fourth point will be 0.75. So number of data points is 5. However, the number of intervals, it's 4. Okay. Fx will be the square of this. So this is 0. This is 0.625. This is point 0.5 is 0.25. Sorry, and this is oh sorry, this is not 0.625. This is 0.0625, and 0.75 square is 0.565. And this is your again 1. So this is your fx. Then you need to use the trapezoidal rule. So area, or you can write this as x square dx from 0 to 1 approximated as h. H is again your 0.25. Okay, from here 0.25 by 2 into initial fx is fx at initial data point is 0, then the final is 1 plus 2 into all sum of the rest. 0.0625, 0.25 plus 0.5625, and you get the answer as I can compute it 0.5 by 2 into 1 plus 0 plus 2 into 0.0625 plus 0.25 plus 0.5625. So 0.34375 or 11 by 32. So the second option. Next, we have solving using the Simpson's rule. So we are given x and fx. We need to find the number of subinterval is 6. So we need to find the area under the curve. So fx dx from -4 to 8. So this will come out to be, so we are given n, so we need to find out h. So that is 8 plus 4 basically. So how this comes out to be is basically 8 minus of -4 upon number of intervals 6. So 8 plus 4, 12. 12 by 6 is 2. Basically, you see the width is basically -4 minus 2, 0. So the jump is of 2. So 2 upon 3 into initial fx is 1, final fx is 14, plus 4 into the second data point. So 3, 3, 4, and 9. So 3 plus 4 plus 9 plus 2 into the odd fx is 4 and 6. Odd position fx is 4 plus 6. So to get this answer as 1, 1 plus 14 into plus 2 into 3 plus 4 plus 9 plus, sorry, plus 4. Yeah. So 4 into, oh, sorry. 4 into 3 plus 4 plus 9 plus 2 into 4 plus 6. So this roughly comes out to be 66, or exact is 66.033. So the correct answer is 66. Assignment 11. Calculate the number of unknowns for the given flowchart. So here you are given this problem statement. You need to find out number of unknowns. So you are not given this term, and this term. Rest all you are given. So number of unknowns are 3. So this is evaporated. So this is the pure, you can say water. This is your pure sugar. So there is no concentration need to be given here. So only these 3 are unknown. Next, calculate the degree of freedom for the following distillation column. So number of degree of freedom NDF is equal to, you can say, number of unknown minus number of independent equation minus number of auxiliary equation or auxiliary relation for a system without reaction, and in distillation column no reaction is taking place. So number of unknowns from here you can see that 1, 2, 3, 4, 5, 6. Okay, 6 unknown are there, and this is useful auxiliary relation. Okay, and minus number of independent equations. So number of components are 2. So number of independent equation will be equal to number of components for a system without reaction usually. So that will be 2. Number of useful auxiliary relation. Useful auxiliary relation. So in order to get your unknowns, in order to find out your unknowns, the useful auxiliary relation are these two. So minus, sorry, the number of unknowns are not 6, they are 1, 2, 3, 4, 5. So 5, and again this is 2. So 5 minus 4, you get 1. So the number of degree of freedom here is 1. So, and in this case, this is NDF greater than 0. So it will have, this is under defined. This will have infinitely many solutions. Okay. Any questions, anybody? If there aren't any further questions, I'll go ahead and close the session for today. I I wish you all the very best for your upcoming exam and all the best for your future as well. Thank you, everybody.